We will in this video we are going to see yet another linear sorting algorithm. So one is called as the Radix Sort and the other one is called the bucket sort. In the Radix Sort we will be using the count sort which is stable. Let's start first with the Radix Sort algorithm.
So let's start with an example. Let's say that we are given 742, 648, 764, 262, 183 and 563. So what I do is that I just look at the least significant bit, that's the last number, so which is basically 28423, okay, and then sort these numbers based on this last bit, that is the least significant bit. So when I do this sorting, so we have to ensure that this is going to be a stable sort. That means that this 774 will be sorted based on the last index, and 262 also is going to be sorted based on the last digit. So both of them have the same number, but 742 is coming before 262. So I have to write 742 before 262. So there is only two numbers which ends with 2. Now let's look at 3. The next smallest is 3. So but 183 comes before 563. So I have to write 183 and 563. The next number is 764. There is only 1 4, and the next number that I have is 8, which is 648. So how did I get this sequence of numbers? I sorted the first sequence based on the count sort. The count sort, the criteria is the least significant bit. Just don't look at the entire number, just look at the last bit here. So now let's look at the next bit, which is the middle bit, which is basically 4, 6, 8, 6, 6 and 4 respectively. So when I do the count sort, we have to ensure that the sort is stable. So what do we mean by that? If you look at the smallest second digit number that you have is 4, and there are two numbers whose second digit is 4. One is the 742 and the other one is 648. So when I sort these sequences, since 7 is written before 742 is written before 648, I should be writing first 642, then I should be writing 648. So then what do we do? So then we look at the next number. There are three numbers with the common middle digit, which is 6. So but first I will write 262, then I will write 563, because 256 comes here, then comes 563, then comes 764. So the next number that I am going to write is 764. So the only other number that is left is 183. The digit it is, so that's the number that comes later. So I have 183. So now again, so I'm going to sort this, apply this again algorithm on the third bit. I apply the same algorithm. I look at the first one. So the first one is 183 because that is the smallest one. So I write 183. Next I should write 263. Then 563, 648. With 7 there are two numbers, but 743 comes before 764. I will end up writing 462 and 764. So what you notice is that the sequence that I have now is already sorted in the increasing order when you go from top to down. Okay. So now we need to understand why this is a sorted sequence, right? So if I take two numbers, this is whose first digit, the most significant bits are different, right? This starts with 5 and this starts with 7. Then it doesn't matter what is written here. The 500 and anything is always smaller than 700 and something. Okay. So if the first two digits are same, then for first two digits are different. Since 5 is coming before 7, because the last step I sorted based on the most significant bit. If you have two numbers starting with x and the other one starts with y, and x is smaller than y, then it doesn't matter what is the other bits. The first number is always going to be smaller than the second number. But if I have the first digit same, let's say that in this case the first digits are same, then what you notice is that what are the count sort that I applied now, the sorting techniques that I applied is stable. So in the previous iteration, this should have been the case that when I consider the second bit, right, so this number should have been the smaller than this. If these two numbers are also same, then the argument goes to the next iteration. In the last iteration, so if let's say that this is also 742 and this is also 744, then these two numbers are same. But so if we go to the next one, in the previous iteration, what I should done is that in the previous bit that you look at, we should have ensured that this is smaller than this, right? So when you compare two large numbers, the rule is simple. If they are same, if they are different, then whichever has the bigger digit, that's the bigger. As long as these are all same, you skip all of them, and when the first bit that you see, whichever is smaller, that is the number which becomes small. So in all these cases, so this was considered in one of the previous iterations, and if the number here is smaller than the number here, this should have appeared before this. And in all the other iterations, when I do the sorting, we have applied what is known as a stable sort. So if this was smaller than this, in all the future iterations, even when all the bits are same here, this number should appear before this number. That's why this algorithm always gives you the correct sorted sequence. So now how do we go from one iteration to another iteration? So we have already said that we can use the count sort here. So when you want to consider 742, what you really need to do is only consider 2. The 2 is easy to get. What you need to do is just look at the percentile, this number, percentile 10, you get 2. So the sorting is based on the percentile 10. So you get the last least significant bits. And the count sort is applied, stable count sort is applied, because if there are two numbers which are the same location, the order in which they are written should be the same, right? Should be the relative position should be maintained. So for the next time when you apply, so you have to apply on the second bit. That's easy to see. You divide this by 10 and then take the percentile 10, you get 4. So if you divide this by 742 divided by 100 and then take percentile 10, you get the digit 7. So it's easy to convert this into an algorithm. So we will use count sort to do that. For completion, let's try to write the code for it. So let's say that I have the C, which is the so we have a variable called C. So I will start my j is equal to 1. So while there is a number of bits, let's call it as k. K is the number of digits in the numbers that I given to you. In the previous example, the k is going to be 3. So what I'm going to do is that first I will say 0 to m. My c is, so my m here is 10 for this example. I'm just trying to use the same notation that I used in the case of a count sort. I initialize my c of I to be 0. Then from I is equal to 0 to n. So what we do is that c of a of I is what I wrote here. But now what we want to do is that we want to divide this by j. J is 1 now. We are not dividing by anything. Percentile 10, right? But in the next iterations, when I come back next iteration, my j is going to be 10, 100 and different things. You will get the different bits that are required. Now I find the cumulative sum as before. Sum I is equal to m to m. C of I plus is equal to C of I minus, right? So this is finding the cumulative sum. This statement is equal to is equivalent to C of I is equal to C of I plus C of I minus 1, right? So this will find all the cumulative sum. Now what I do is that we are writing back to the array B, which is from 0 to n minus 1. B of, so this is exactly the same as before, C of A of, I am not looking at A of I, so I should always compare A of I divided by j percentile 10. So whichever is that number at that location, so B of I should be at this location, we should be writing it as equal to A of I. So once we are done with this, we can write it back to A, because what I need is A. So A of I is equal to B of A of I is equal to B of I. When I come back to the next iteration, the k will be decremented by 1, but I named the next bit. Next bit, when I come back, I want the next bit. Next bit is obtained by just updating my j to be j into 10, right? So initially j will be 1, so when I divide 742 divided by j, if I do percentile 10, in the first iteration what I am going to do is that I am going to divide by 1. So when I divide by 1, so in the first iteration when j is equal to 1, so what I am going to do is that I am going to get 2 here. In the next iteration j is going to be 10. So when j is going to be 10, so I am going to do 742 divided by 10, what I get is 74. If I do percentile 10, I am going to get 4. And when in the next iteration j is going to be 100. When 744, when I divide by 100, so what I am going to get is 7. If I do percentile 10, again I am going to get 7. So in general, so in the kth iteration, so what I really need to do in order to get the kth bit here, let's say the kth bit here, so what I need to do is that I need to look at a of I divided by 10 to the power k, right, and then take percentile k, where k is going from 1 to let's use a different notation. So maybe so in the ith iteration, so when I go this is 10 to the power I, where I is going from 0 to some k number of digits. Okay, so depending on the number of digits in every time when I just dividing by 10 to the power I in the ith iteration, so taking percentile d, I can refer to the ith bit in the sequence. Okay, so this is what is called as the Radix Sort. The complexity of this is k times we are applying the count sort, which is order n. So where k is the number of digits. So this is n into k. So if you look at if I given you, let's say 10 to the power 6 numbers, each of them is a telephone number, right, 10 to the power 9, then the count sort itself cannot be applied, but I applied. So since the number is only a 10 digit number or a 10 digit number, then you can apply Radix Sort so many number of times. So 10 times you can apply Radix Sort, which is essentially applying the count sort 10 number of times. The number of digits here is k here, right? So by applying 10 times the count sort, you can still sort the sequence. Since 10 is a constant, the k is a constant, this is order n into k. In general, this is also used for sorting text, right? So if you're given some words and you want to sort it alphabetically, then so what really matters is that our k is the largest word that is given to us. So if that is a constant and r2 else, then we have an algorithm which is order n into k. So let's consider the previous numbers that we had written. So the numbers that we had are 742, 648, 764, 262, 183 and 563. So what we did is that we looked at the least significant bit, we sorted based on this, and then we went to this, we basically went from left to right, right to left. So now let's say instead of starting at the least significant bit, let's start sorting this based on the most significant bit. So when I start sorting on the most significant bit, the first number that I am going to get is 183, and the second number that I am going to get here 262, and the third number that I am going to get is 563. The next number is 648, and there are two numbers. With 7 there are two numbers. I will maintain the stable sorting. I will write it as 742 and 764. So what you notice that in one iteration itself I got the sorted sequence. Okay, so but what could have happened is that I could have started with 764 here and 742 here. In that case 742 and 743 could have been not in order, but in this case this is already sorted, we don't have to do anything. So what you notice here is that if I sort it based on the most significant bit, see if the bits are same, if you take any two numbers, if the first digits are different, then these two numbers are already in the sorted order, right? So the first number is anyway going to be smaller than the second number. But if the first bits are same, that means that in second onwards we don't know anything, right? So what we can do is that so after if the among all the numbers, after we do this partition, this distribution, you only consider the numbers which are where the first bits are all same, and then what you can do is that you only need to sort them and then concatenate with the rest of the list. You think about all the numbers which starts with 1, you sort all of them. If there are several numbers which starts with 1, you sort all of them, ensure that all these are in the sorted order, and then what you do is that you take all the numbers which starts with 2, right? So then you sort all of them, so then concatenate to the list that I had, then you look at all the numbers which starts with 3. See, anything which starts with 2, so I am assuming that all the numbers have the same number of digits in it, otherwise we are basically going to do AFI divided by so the 10 to the power, so you are going to do by 10 square here. So if it is a k digit number, you are going to divide this by 10 to the power k minus 1, so that there is only one digit left here. So this number is anyway going to be smaller than this number, and anything which starts with 4, 5, 6 anyway is going to be smaller than 3. In general, so if you just make it as this is called bucket sort. So all the numbers which starts with 1, you are going to put it in the 10 buckets. So what the problem here is that if you have too many numbers and you just create 10 buckets, then there will be several numbers in the same bucket. Okay, let's say that you have the numbers which are as big as 10 to the power 9, but let's say that I have created 10 to the power 6 buckets. Okay, so this number, one way to distribute this into buckets is such that I divide this by 10 to the power 6. 10 to the power 3, right? So basically I look at the first, let's say that I look at only the first 6 digits. So based on what is the first digit, I am going to put it in this bucket. How do you maintain this bucket? So there are two numbers which falls into the same bucket. What I could do is that I could create a linked list there. And so anything which maps to this, you can put it in the linked list, right? So what I am basically saying is that if I give you the telephone number which is a 10-digit number, just look at the first 5 digits and put it into this bucket. That's right, this is 96421. Then you put this into the bucket which is 92421. And among all the numbers which are there in the same bucket, you sort it using some brute force algorithm. Assuming that if there is a way to distribute this numbers into different buckets, so that in each bucket you have only constant number of numbers, and you can sort these individual buckets using a brute force bubble sort algorithm, which is only going to take constant number of amount of space, and once you do this, then you just concatenate, go through the list from here to here. Each of the list is sorted. You just put the numbers in the same order. You get the sorted sequence. The bucketing should be in. So there are two conditions that should be satisfied here. Anything which goes into this bucket, so the ith bucketing should preserve the sorting property. Anything which goes here should be smaller than anything which goes to the next bucket, right? So the bucketing should be such that anything which goes to the location here should be smaller than the anything which goes to the next bucket. If this condition is satisfied, and the bucketing has a nice property that in each of these buckets you have only constant number of numbers which maps to each of these buckets, then you can sort individual lists and then concatenate all of them. You get the sorted sequence, right? So putting them, distributing this into each of these buckets is only going to take order n time. After that, since each of the buckets have only constant number of numbers in it, sorting it then using a brute force algorithm also takes constant amount of time. So this entire algorithm will be the linear time. But this may not work all the time, because if I give you all the numbers, right, so which starts with 1, 6, 4 to 1, and here I can write anything, text next to each number can be anything. I can still give you 10 to the power 6 numbers which are all mapped to the same location, right? So if I give you numbers which are all mapped to the same location, then you have to, so that this does not distribute into the different buckets equally, right? So that's the problem. in that case we can't use bucket sort, right? So bucket sort can be used so that in such a way that you can distribute these numbers into different buckets such that the numbers which goes to the ith bucket is always smaller than number which goes to the I plus 1 bucket. This is true for every bucket, and each of the buckets get exactly only the constant number of numbers, so that each bucket can be sorted with using a brute force sorting algorithm and then concatenate everything, right? So going back to the example that I gave you, is if you divide the 10 to the power 10 a telephone number, if you look at the first 5 digits and the second 5 digits, your bucketing could be based on the first 5 digits. The number which goes rates at 96421, so can go into the 9642 first digit, right? So that bucket. If there are several numbers which goes to them, all of them will be in the will be linked by a linked list. Okay, so this is the one example of doing the bucketing. Given depending on the data, if you can define a bucketing mechanism so that the two properties that I mentioned satisfies, we can do sorting in linear time.
In this video and in the last video, we have seen that in some special cases sorting can be done in linear time, but in general the sorting requires any comparison based sorting algorithm requires n log n number of comparisons. In the next video, we will come back to what is known as heap sort, which will also sort a given sequence of numbers in n log n number of comparisons.